inference on a least squares regression line. So the end game for this is to be able to come up with a confidence interval and to do a hypothesis test for the slope of a least squares regression line. All right. We're going to learn about checking the conditions. There's an easy acronym for it. It's LINER. It's not that bad. Is it linear, independent? We'll check for if it's normal. And then, forget. I have it written down. I haven't done a problem yet. Gotta do one. It's been a year since I've done a problem. So we're gonna look. We're gonna be asking questions such as: is there really a linear relationship between x and y, or does it look like there's a positive correlation just by chance? And we'll look at how much a predicted value of y changes for each unit x. And I don't know if we'll look into the margin very much. We just have to be able to perform to just do inference, okay? All right, so for instance, we have a scatter plot. Their example is a scatter plot of eruptions, right? And so they have a duration of each eruption as we go on, and then how long it takes until the next one. All right. But just reminding us what's going on with these squares regressions data. It turns out that if you look at different spots within that larger regression pattern, or that larger scatter plot, you could say, that within these different durations, you wind up with these different slopes. You have slope of 10.2, 7.7, 9.5. So the question is if there's all that variation in slope for each different segment, what can we say about the true slope, right? The actual population slope, the slope of the line that matches all possible geyser spurts or whatever. So we're looking at the sampling distributions of the slope. So of B, we're talking about the slope of the least squares regression line. This is just similar to slide. I'm trying to just breeze through this because you don't have to get super crazy about looking at the sampling distribution of the slope of the true least squares regression line. You don't have to get into that too much. What we just have to be able to do is read a mini-tab output and input the proper values into a formula, honestly. And we're going through the same kind of process that we've gone through for every single one of these distributions. Right? We look at the center and the spread and the shape. If we were to take many samples of the same size, in this case, this one is 1,000 samples of the same size. So turns out that the standard deviation is pretty close, right? It looks symmetric and unimodal. In other words, it looks approximately normal. It looks like a normal distribution, right? So some formulas. We're looking at the sampling distribution of a slope. Remember, we've got a predicted y, or a y hat, equals a plus beta x. So we got a new variable in here, this beta, and beta is just the slope of our least squares regression line. It's the true slope of our least squares regression line. So beta is a parameter. And we use the slope b, right, this little b, we use that to estimate the parameter beta. the mean used to be is beta. Our mean slope is going to be beta. And then we have a standard deviation, and of course your 10% condition has to be satisfied in order to use this formula for standard deviation. The thing about this standard deviation is this is the standard deviation of the population, right? The sigma on the numerator. So we're actually going to use a different formula to calculate the standard deviation because we more often than not are going to not have the standard deviation of the population. So we'll say it's approximately normal if the values of the response variable follow a normal distribution for each value. And what we're really going to be looking for is that there's not an extreme amount of variation in y values as we increase x values. If the variation stays the same, that's okay. But things are going to be weird if we have a high amount of variation in our y values as our x values increase. And I'll show you exactly what that looks like. This is a really cool picture. This is what the distribution of your y values is. Looks like that, right? Imagine you have a y coordinate, an x coordinate, right? And then you have these, like, for each x coordinate, you have this normal distribution looking in there. It's kind of cool. Imagine a normal distribution is kind of popping off the page. And we're going to look at what it looks like for our distribution to be normal. That's what it was. All right, so here we go. In order to perform inference on the slope, you have to first check these conditions. Is it linear? Does it appear to be linear? The scatter plot, right? Your relationship between your explanatory and your response variables. Are they independent? Fairly easy to check. Is it normal? And we'll be able to look at that using a number of different graphs. So in order to check for normality, you can use a regression output. It's probably going to be the best one. It's going to be the most convenient one to look at. Or you could look at a standard normal probability plot. Those would be the best. I guess they do put a histogram on there. I'm not sure that I would really necessarily use that. I think that those two graphs are the best. Look at your residual plot. If you don't see any strange patterns in your residual, then you could assume normality. And then the standard normal probability plot is the best because it's going to give you the most exact value, or the most exact picture, I should say. Equal standard deviation. So what we're going to look at for this equal standard deviation is that as I go to this lower x value, if the variation is really small, and then I go to a higher x value, the variation is really big, that's going to be suspect that it doesn't match, or it doesn't, the conditions will not be met for inference. And then, as always, the data has to come from a well-designed random sample or experiment. So it spells liner. I'm in the middle of editing the this thing right here. And you'll see, and everyone gets one regardless of you're taking the test or not. And it has all of these. Actually, this one uses LINs, linear independent normal distribution, and standard deviation about the same. This equals standard deviation is taking the place of the S in here, but you do have to check that it's random, but I think we always check that, right? And then you got your phantoms in there. And it was pointed out, I updated it for the new, the latest edition of our stat book, and I think there were some errors, so I need to update it for you guys. But everyone will get a beautiful study. So if we're going to check, I talked about it, right? I said all of these, right? We're going to see if it's linear, again, we're going to look at the residual plot, right? Remember, in our residual plot, if we see any type of, like, if you see like a parabola or something that definitely doesn't look, if there's a set pattern in the residuals, then we're going to assume that the data is non-linear, okay? We'll actually talk about how to do nonlinear data in 12.2. So basically, it's stem plot, histogram. You can also look at the residual plot as well. The normal probability plot is the best. And it's pretty easy to get that from your calculator. Or, if you're not going to get that from your calculator, it's usually going to be given to you in the question. You'll see a normal probability plot in the question. And then you can refer to that normal probability plot. We're looking for the equal standard deviation. So we would look at scatter of the residuals. You can actually look at the actual scatter plot and be able to tell as well. But if you see that your residuals are, I'll draw a picture of this again tomorrow. But if you're looking at a residual plot, right, this is 0. If you see right that as your x values are increasing, your residuals keep getting larger and larger and larger. There's probably going to be a picture here. That's what we're looking for. And I have a really nice picture of it that I'll share with you. All right. This is not super important. Just these things. So what I was saying. So the spotting paragraph. Since our sigma, right, is the standard deviation of the population, we're not going to have that. So instead, we're going to use this x as our standard deviation, and it's calculated by looking at the residuals. I really don't anticipate you're ever going to have to calculate that. What you're going to have to do is find where this value is located, the standard deviation of your slope, on a mini tab. We're going to look at that. So we're going to estimate that is the same exact slide. All right. All right. So this is what our standard deviation is. If we're able to get that standard deviation, we can get a z-star. That is only if we have the standard deviation of the population of all possible slopes, which is not really going to happen. So we're going to always be using a t distribution. I should say almost, but I can't imagine that you wouldn't use a t distribution because you've got a sample every single time, right? When you're looking at a scatter plot, we're looking at a sample, and most often not the entire population of possible values. So this is our critical value that we're going to be using. This will be our test statistic that we'll be we'll get a t value from that. It's not a test statistic. We're going to get a t value from there to get critical values. Our test statistic is going to, this is just a t value for it, right? So it's going to be our slope of our least regression line minus the slope of the true least squares regression line divided by the standard error of our slopes. And that's not, we're not going to use that. We're going to use this. This is where it's at. Okay? So here we go. Now we finally got down to the nitty-gritty. Nitty-gritty. We're going to, and this is what we need to do. All we need out of 12.8 is to be able to create a confidence interval, interpret it, and to be able to perform inference on the slope of a least squares regression line. And we'll do one of these tomorrow. They're really not bad. You get information from a Minitab output, you plug it in there, you create an interval. If 0 is located in the interval, then you're going to think that you're going to conclude that that least squares regression line is maybe not a good representation of that, or that there's not actually a relationship between our explanatory and response. Because if a 0 slope is included in there, right, then you can't say that there's actually a positive relationship or a negative relationship between your explanatory and response variables, right? You would like to see some sort of an increase occur or some sort of a decrease, which would be denoted by a positive slope or a negative slope. So if 0 is in that interval, then it might be the case that there isn't any type of relationship. I highly doubt that you'll ever have to calculate the standard error of the slope. We'll look at it when we do some examples. All of the examples I've seen have given you a mini tab. All right, so we're doing inference. Here we go. This is our test. So our statistic minus our parameter. And when we come up with a null hypothesis for this, our null hypothesis is always going to be that beta is 0, right? We're going to say that, hey, we're going to test against the idea that that the slope is 0. So if the slope is 0, then we can't say that there is a relationship between our explanatory and response variables. So that is what we're going to be trying to do. And it's been written here a bunch of times. I mentioned it, right? Instead of n-1 degrees of freedom with least squares regression inference, we're going to use n-2 degrees of freedom. All right, so same deal with two-tailed I mean, we're really not doing anything super new. We are just using a new formula. The process is staying the same. And that was it. That was it in a nutshell. I think you're going to get so much more out of us doing some examples than you would from us, from really describing the distribution, the sampling distribution of B, the slope of our least squares regression line. I think we should really just get into it. And I'm not sure that we actually did this. Interpret the values of A, B, S, standard error of the slope, and R squared in context. We did a lot of this stuff back in the day when we were looking at bivariate data. the first time and coming up with a least squares regression. So there we go. Let's get into some examples.